Seguimos ahora con la exposición de Karthik Iyer, titulada Modeling Sills Intrusions in Sedimentary Basins from Petroleum Systems to Climate. Modelado de intrusiones de filones en cuencas sedimentarias desde los sistemas petroleros al cambio climático. Karthik Iyer tiene un PhD de la Universidad de Oslo, donde combinó petrología, geoquímica y modelos numéricos para investigar las interacciones fluido-roca. Profundizó más en los modelos numéricos durante su postdoctorado en Geomar, en Alemania, donde se centró en comprender y modelar el flujo de los fluidos en los límites de las placas. Sus principales responsabilidades en Geomodelling Solutions incluyen el modelado de sistemas petroleros con un enfoque especial en los márgenes volcánicos y la combinación de análisis de datos, técnicas de optimización y modelos impulsados por procesos para cuantificar estos sistemas. Karthik, the screen and the micro is yours.
Thank you, the organizers, for inviting me here. I hope you all hear me. And I'll just share my screen right now. I hope you guys see my screen.
Yes, it's perfect.
Okay. So once again, thanks for inviting me to give this talk. And thanks also to Ben for a great first talk. He laid a very good foundation for my talk indeed. And maybe I also hope to answer some of the questions you had there during this talk. So magmatic intrusions, we've heard a lot about it from Ben already, but I'll quickly touch upon why we need to care about them, especially if we're dealing with petroleum systems, which I assume most of you who are listening are. So one simple effect is you put a hot body in, like a magmatic intrusion in sedimentary basins, and if there are source rocks lying around it, they're going to just mature and generate hydrocarbons, which is of great interest. Okay, not only that, if you have a sill body in there or a dike, any magmatic intrusion, it can affect migration. If it's impermeable, the fluids will want to go around it, so it'll form a barrier and affect how fluids migrate through your basin, or where they fracture the sedimentary rocks due to a boiling of fluids, of pore fluids, water, for example, or generating methane and other gases. This can increase pressure, fracture the sedimentary rock, and create new migration pathways. Besides that, it can also affect reservoirs. It can act as a reservoir itself, in the case where we've already seen in Argentina itself during Lassi, that the sills cool down, fracture, and then the hydrocarbons migrate into the sills themselves and stay there. So it acts as a quasi-reservoir. Also, if
I'm sorry, Karthik, please, could you talk a little louder? Because
it's too loud?
Yes.
Okay, yeah,
and turn on your laser pointer, please.
Yeah. I will try to speak softer. So where was I? Yes, reservoirs. And if there's a pre-existing sandstone reservoir nearby, close to a sill here, for example, if it already contains hydrocarbons, for example, oil, the heat generated by the sill will crack that oil to form gas. So that can change your system again. It also can form seals or traps. For example, in the Parnaíba Basin, if I'm not mistaken, in Brazil, the sills form dome-like structures or four-way closures, which are impermeable, and any hydrocarbons that are generated by sills lying below that top sill migrate into the trap, and the sill actually seals it. And if hydrothermal fluids are moving around, like Ben has already showed us, these hydrothermal minerals can precipitate secondary minerals. And these secondary minerals can clog up pore space and create additional seals. And lastly, but not least important, is that all of this gas that is generated can escape into the surface or the sea and can change the chemistry of the oceans and also the paleoclimate. And we'll take a quick look at that as well. So, but in order to understand the effects of these intrusions, we try to model them, because we can to some extent go and look at it in the field, but we cannot really quantify it as such. So for that, we need models. So how do we model such a nice picture? This is from El Manzan. This is from our trip to Lasi in Argentina, where we have sills going through oil-prone or hydrocarbon-prone source rocks, and we try to model them. But first, in order to model them, we have to take care of the physical processes that control the effects. And the simplest process we need to take care of when we model sill intrusions is heat conduction. So energy comes in with the sill and then heats up the surrounding rocks. So the sill cools, heat is transferred to the surrounding rocks, and there are numerous effects associated with it. That's the simplest variation. For now, we'll just ignore fluids or advective heat transport with it. What controls the energy transfer between this in this system? This is a simple equation. Don't have to worry about it. But what it says that the transfer of heat from one place to another is controlled by the rock properties such as density and heat capacity shown here, and the conductivity of the rock. So that will control it. But we also have this Q term here, which signifies any heat sources, additional heat sources. For example, the latent heat of crystallization. That's an exothermic reaction that occurs when the melt that comes into the sill crystallizes and goes from melt to solid rock. That generates a lot of heat and adds to this energy input here. On the other hand, when the heat is transferred to the surrounding country rocks, different reactions can take place. Minerals can dehydrate, pore fluid can boil, and these are endothermic reactions. That means they take in heat. So we have to account for all of these different physical processes at the least to try to better understand what's happening in the system. So this is just a simple sketch, not a sketch, this is actually a model, but it's a simple way of visualizing what happens when we deal with these different processes. In the left plot on the y-axis is the highest amount of temperature that is experienced at a distance along the x-axis away from the sill. So what I'm doing here is I'm placing a sill here and at 1100 degrees, and it has some heat capacity, and I see what sort of maximum temperature I feel away from it. And this is in percent thickness. So this is one sill thickness away, and this is 2 sill thicknesses away, 100% and 200%. This is the plot for the same results for the model, but in maturity. So maturity basically tells us it's based on Retronite reflectance and is used to sort of measure whether we're producing oil or gas or we are too mature. It's basically cracked out. Then we can see there's a correlation between the distance from the sill and the energy input into it. In this case, the gas window extends up to 65% of the sill thickness and then decays into more or less immature rock more than 200% away. So the first obvious thing is, how do you change heat input? Maybe it's not a diabase sill, or even if it's a diabase sill, it's something has happened to the magmatic system and the energy of the next sill or the third sill is lower. So if you lower the sill temperature, total energy is lower. Therefore, you have low maturity away. Pretty straightforward. What happens when we change heat capacities? Do we know that? Well, it's not very well constrained, but we sort of know what heat capacities to expect in our cells. And based on that, you can see if I just increased the heat capacity in my model, I increase the energy input. And then I have a greater impact on the host rocks further away from the sill, and I generate more gas in it. And lastly, like I said, the sinks, the sources and sinks are pretty important. The latent heat of crystallization, again, I'm going back to my base model here, sill temperature of 1100 and the same heat capacity. but I just introduce the process of, I quantify the process of latent heat or crystallization, and adding that adds an equal amount of energy into the system as significantly changing the melt heat capacity. So you see that just small tweaks in a simple model in properties makes a big difference. So we need to get that correct. And one way of doing that is to test our different inputs for the model against measurements such as Retronite Reflectance, which records time and temperature. So those were the key processes, but it's also a question of scale. When we think as petroleum system modelers about scales, we usually think these dimensions. So this is a nice model of the North Atlantic margin opening. Here there's oceanic crust forming, a lot of heat being generated, and we have basins forming, rifting occurs, and you have everything that is associated with a full basin model. But this, as you also notice, is occurring over tens of millions of years. And the scales we're talking about are, in this case, thousands of kilometers. And if we look at our usual sills, a pretty thick sill is a few hundred meters, but usually they're not even that. They can even go to meter scale. And when we try to model that, this is a 100-meter sill and placed in a cold rock. We're talking about days and years and sub-meter scale resolutions. So these two resolutions are sort of incompatible with each other. If I use this kind of model to try to figure out what's happening when a sill is in place, I'm going to get very different answers than I should, because I've not done it properly. That was sort of illustrated in this paper by Bulguroglu and Milkov, I think it's 2020, where they looked at 1D models where thin and thick sills were emplaced. And they had a few Retronite reflectance data. I apologize for the quality of the figure, but they're not mine. And they tried to model these sills. But what they did is they used a modeling tool that is generally used for basin models, not sill models. And using this tool, they figured out, okay, they said thin sills have very, very big aureoles, 276 to greater than 1,000 times the sill thickness than thick sills, 31 to 137%. And based on physical processes alone, from general physics, you cannot explain these large aureoles here. Generally, sills tend to have aureoles between 50 to 200% of their thickness, because it's all property dependent, like I showed you, and process dependent. The curious thing about this paper was that it seemed that the conclusion that thin sills have very large aureoles was based on the model results only. There was no physical process defined that actually does that. So we were a bit confused. And the last clue was that these lines that pass through their Retronite data look very jagged. They're not smooth. In the purely conductive system, which this basin model tool is, you would not expect such jagged lines. They would be smooth because heat diffusion is a smooth process. So we went and took a look at it and published a comment on it. So we took it into our own sill modeling tool, Sill1D, which also takes care of the entire basin processes like diagenesis and maturation due to burial prior to sill emplacement or after sill emplacement, but also resolves the thermal effects of sills correctly, because you need to take care of the time and space resolutions there. And I'll illustrate that now. These are the Retronite reflectance data from their paper, and this is their curve that was published, where they say these thin sills have very large aureoles, which are defined by these points here. We took it into a model and purposely made a very low resolution model. And as you can see from a low resolution black line, that we also somewhat get their results. We don't know what resolution they exactly used. It was not defined, so we had to make up our own, but we used the low resolution. which we knew was not really suitable. But we are also getting very, very thick aureoles for the thin sills. But if you do that with the resolution that a sill requires to study the effects of these intrusions properly, you get a proper diffusive curve around these sills. And then you still get a similar match or very close to that match in Retronite reflectance, but that's not the point. The point is that if you model it correctly, you don't get this conclusion that thin sills have a very, very big aureole compared to thick sills. They have an aureole proportional to their thickness, and it's simply physics that determines it. So it's not only processes. If you're modeling something, you have to take care about the time and space resolutions as well, especially when sills are concerned. Enough of the processes now. I'll just show you some examples of 1D models. We'll start out simple, but I kind of like 1D models. They're easy to understand, they're very easy to set up, and they're very, very fast. So when they're very, very fast, I can test thousands of scenarios in very little time. The thing is that in 1D models, you're restricted to a purely conductive setting. You cannot really add fluid flow to it because you need more than one dimension to accurately resolve the effects of fluid flow. This is an example of all the wells we have where I usually work in the on the Norwegian continental shelf. And there are hundreds of old well logs here. And some of them do, like Ben has mentioned, in the Norwegian Sea and also in some parts of the Barents, we do have volcanics intruded into the system there. And 1D models are also good because when you do a 1D model, you can calibrate very easily. You can compare it to what we actually observe in measurements using a 1D well log, for example. So the correlation is pretty simple as well. And then you can benchmark and ground your model in reality. This is one of the examples from the Norwegian Sea. This is 660752, and it's from the same region that Ben was talking about in his previous talk. And this is the Utgard, and this sill passed through the Paleocene, the Cretaceous, and 2 sills. So we can easily set it up in our modeling software. It's very simple. We did not tweak anything. We just took textbook properties. We did not change anything specific to the system. And then we modeled. We just straightforward modeled it. I just have to change to the regular pointer now so that I can run this video. And what we're seeing here is the initial state prior to sill emplacement. So what the sill model does, it solves for temperature and Retronite reflectance, etc., in the system based on a normally subsiding basin. So we're calculating it for the thermal gradient we prescribe, and sediments are being deposited. And now we intrude sills. And previously, when I was depositing sediments, that occurs in million-year time steps. Now we're down to minutes initially, then days, tens of thousands of years, and when the sills really get cool, it goes back to normal basin scale timescales. But it is very important to resolve that, otherwise we will not really match any of the Retronite data we have. And the Retronite data we have here is pretty good. It's not only 5 scattered points, which in our opinion at least does not give you a full picture. If you really want to resolve what's going on in the background and by the sills, you really need to take care where you measure Retronite. So we have ample number of data points and we can match it pretty well, just using a simple 1D model. In this case, we also match the TOC content, how it depends on the heating, how it degrades due to the heating of the sill. And if you assume some HIs, you can also determine using a more complicated organophases method and full kinetics, how much oil and gas could be generated near the sills. Speaking of hydrocarbon generation, you can also visualize it in this method. Here I'm plotting time and oil volumes and gas volumes stacked. They just stacked on one on top of the other so that we just visualize it better. And as you can see, the deepest one, the Quitness Formation here, is generating oil initially, but that's simply because of burial. And suddenly the sills come in at 55 million years at the PETM. And then this huge jump, it kickstarts hydrocarbon generation, both oil and gas here, and drives the entire system to completion. So a very important effect on hydrocarbon generation in the system. But besides hydrocarbon generation, like I mentioned in my introductory slide, it also has effects on reservoirs, or could potentially have effects on reservoirs. So we can also look at that or try to quantify it by just looking at the temperature history of what happens at this point around 3.6 kilometers depth in a model. We can extract the temperature history. So temperature is increasing downwards now. So nothing is happening here. That's because this point does not exist till then. This point comes into existence here at around 84 million years. And then there's burial. It's progressively gets buried. There's a different sedimentation rate. Then suddenly, bam, the sills come in. There's an increase in temperature. But on the basin scale, you also see the time scales are very different. This is just a quick spike, and then it returns back to normal because the cooling of the sill is very, very fast compared to the basin generation. And then we can look at if it had any effect in terms of, for example, in this case, quartz cementation. It's also a kinetic reaction. We put it in one of our other tools, Diagen, and we see that nothing really happens. It's just, this is porosity I'm highlighting right now. It's just mechanical compaction. Even though there was a spike in temperature, in this case at least, it did not alter or affect significantly how quartz cement is formed or affect porosity. So in this case, we can go and say, all right, look, if a reservoir is there, we're pretty safe in terms of cementation. In terms of opal A, CT, and quartz transition, there's a different picture. Here we have opal A transitioning to CT due to burial, but that quickly changes when the sill comes in, and suddenly there's a transformation from opal CT to quartz there. And the same thing happens with smectite to illite transition. Again, the sills are the main drivers. Quartz cementation didn't occur in this one because although there was a temperature increase, it was relatively short-lived. Let's look at another point here. It's slightly closer to the sill. And if your reservoir is there, you again have this spike in temperature, but it's a much bigger spike. It goes to 400 degrees. And even though it's short-lived, now we start seeing the effects of quartz cementation there. There's again burial, decrease in porosity, and porosity basically goes down to zero because everything is cemented because of this increase in temperature. So if my reservoir was this close to a sill, then not only does it affect maturation across it, it could completely destroy my reservoir in this region, potentially. That, in my opinion, at least, was a relatively simple 1D model. Also because not only because it's a 1D model, because it has just two sills. So it's very easy to just tune it to myself, say the emplacement timing, the temperature, and try different scenarios and match my Retronite data. But we start getting into sort of not trouble, but yeah, it takes a little bit more time if you have all these parameters to tune. Suddenly you have 10 cells being emplaced. The emplacement is at 55 million years, but plus minus 200,000 years. And as you can see, as I've already showed you, the processes, how they cool is within years, not tens of thousands of years. So even though we have a plus minus sign error bar on our emplacement time, it's not good enough to really figure out how these interact with each other. And in this case, at the West Balkan province, volcanic province in the Barents Sea, we also have erosion. That also affects how Retronite reflectance is changed overall, because any erosion with progressively, any basin subsiding will progressively increase in Retronite reflectance, but if you erode it, suddenly you have very deep sediment sitting on top, and it will not match your general picture of how it should look like at that depth. So we need to account for that as well if we want to match any of our measurements. And in order to do that, we combine the sill tool with an optimization function, a global optimization function to be more precise. And what this does, it takes in various inputs. So our inputs for the sill model are erosion, the paleothermal gradient, and anything associated with intrusives such as emplacement timing and emplacement temperature. So these are variables we don't really know, and we can't possibly test out all combinations by hand to best match the Retronite reflectance we observed there. So what this model does is it keeps feeding the sill model with the combinations of these input variables. The sill model runs through it, figures out what the Retronite response is, calculates that, and sees what the fit is to data. I just have to move back. And once it figures out what the error is, it transmits the error back to the optimization function. And using gradients, the optimization function tries to figure out how to quickly converge on the best fitting result. So as an illustration, I've just taken thermal gradient and erosion here. I've not taken all the different variables because it'll be too many dimensions to visualize. And what it does, I'm seeding different points, and the minimum is actually here. And you have other local minima everywhere. But what we want is to end up here. And this is what the optimization function does. It tries to figure out, using the error obtained from the sill model, converge on the best fitting input variables there. So even for complicated models, we can combine it with these optimization functions and try to obtain a pretty good fit here. So in this case, we obtain some erosion amounts for the different events. We got a paleothermal gradient that agrees with our background Retronite reflectance, and it also gave us different sill emplacement timings and temperatures for the 10 different sills we had here to best fit the reflectance curve here. I should mention that this method is if you want to know more about it, we recently wrote a paper to estimate erosion in sedimentary basins in April this year. So more info is there. So in order to summarize, I really like 1D models. They're very easy to set up. They're very easy to test. And you can then combine it over a large scale to see what's happening on a basin scale. So, and even for complicated algorithms, we can, complicated models, we have these multi-objective algorithms we can combine it with to try to figure out what's the best fit there. But what about fluids is what Ben would probably say right now. And the fluids are important in cases such as the Warren and Mora basins that we have just seen. There are numerous expressions of it in the seismic. So these vent structures there that are usually associated with sill tips and on the seafloor. So what about them? In some cases, they're pretty important, and we should also take care of that. And 1D models, like I've said, cannot really deal with that. So then we have to go use the second dimension. This is an example from the Harstad Basin, also Norway. There's Norway, there's the Harstad Basin, and this is the region we're looking at. This is also in collaboration with VBPR and Shell. And we published this paper in 2019, where we looked at a sill complex, shown here in red, that has intruded in the Cretaceous. And the seismic here has been flattened on base vent. You know all these terminologies now. And in the seismic structure, you see there's disturbed sediments here, which terminates at this base vent horizon. So that's what builds up a model. We have our general equations, which solve for conductor flow, but now we turn on the fluid flow or advective heat transport model as well. and we initialize it to the steady state background temperature. There's maturation that can be calculated using the E0 method. And what we do here, right now at least, we calculate the maturity based on E0, and anywhere it's above 1, that means it's above, if it's within the gas window, we convert all carbon in the TOC to methane. And that methane is simply transported with the water in the system. It's a very simple model. There's no multi-phase flow in this because that would be too expensive, but it's a simple model to start with, to see whether we can recreate this vent. Why does it occur here? That was our main question. So let's go back, and I have to switch my pointers again. Lots of videos. So we look at a setup where we have low permeability. Low permeability because we have a permeability structure in the sediments for sure. It decreases with depth because of compaction. Porosity and permeability will do that. But we really don't know the values what should be there. We don't have extensive borehole or many studies looking at that here. So, okay, that is one of our unknowns. The sills in this case are impermeable. And what I'm plotting here is temperature and Retronite through time in the video. So I'll start running in a minute. You can already see that prior to sill emplacement, this has been initialized to the background temperature state, so steady state temperature and background Retronite reflectance that has been pre-calculated already using this thermal gradient. So I'll just run the model. As we can see, since it's very low permeability, fluids are not really free to move, even though there's a lot of energy being pumped into the system. And basically what this returns is a conductive model, more or less. There's a lot of interesting interactions here. Where sills get close to each other, there are increased maturation. I'm sorry, I'm just going to use the hand now and not the pointer because I have to keep switching. But this, more or less, this picture you could more or less get away with a 1D model. So low permeabilities are not doing it for us. It does not recreate any vent structure here. So, okay, we go to the other end. We increase the permeability. This is the high permeability system now. What I've just done is just increase the permeability structure. There's still a dependency on depth, but I've increased the permeability structure by a couple of more orders of magnitude. I'll just run this again. And now we start seeing a lot of hydrothermal vents forming. And as you can see, they have this spacing to them. And this is typical for hydrothermal vents. They'll form many, many vents when they're small, but the large ones coalesce and compete with each other. And then they have their own individual spacing, which is determined by the permeability and porosity structure of the background. So that could maybe answer one of the questions, why you have hydrothermal plumes in the middle of the sill. It's probably also because it's not one of these explosive ones, most likely, but it's more hydrothermally driven, where it just wants to go up and is determined by the entire permeability structure or the flow structure in the system. But again, these are more or less 1,000-year timescales. They're pretty slow. And if this occurred everywhere, if this kind of system was present, we should have been expecting to see hydrothermal vents everywhere in the seismic with perturbed sediments everywhere. But we only see them here at the tip of the sill. So that was not working as well. But we also knew that overpressure could potentially be generated either due to boiling of pore fluid, which is water, brine, that creates gas, and then you expand it and then fractures, increase fluid pressure and fracture the rock. Or we also know that a lot of gas can be generated from organic matter very suddenly due to sill intrusions. And then all this gas has to go somewhere and increases the fluid pressure, fractures the rock, and could generate its own permeability. So in order to do that, we implemented a simple fracture criteria where we increase the permeability if the fluid pressure was greater than the lithostatic. And that's very normal. If you reach lithostatic, you frac, you generate fractures and things escape. And it's a quadratic term here. And every time the fluid pressure increases, we increase permeability. And once the fluid pressure decreases, because the fluid's allowed to escape out of its newly formed, due to its newly formed permeability, it is reduced back to the background because you have the overburden there, and it will also result in compacting and closure of these fractures. So let's see what happens going back to the same high permeability case that I just shown you, where we had numerous hydrothermal plumes. Now I'm showing you temperature here, and the permeability structure here goes in its log. So it goes from 10 to the minus 12 to 10 to the minus 17 on the bar here. And if you can spot it, you will also see a red overlay on it. And that red overlay shows you where fracturing has occurred. Just quickly run through it. If you were quick enough, you would see a red overlay here, which quickly disappeared, but now nothing. And what we also see is that we get the same picture back as in the case where we not introduced this fracture permeability implementation. And that's simply because the permeabilities are relatively high in the system. So any overpressure or any gas that is generated there will be quickly, the fluid pressure will dissipate so quickly because of the high permeability that it cannot be sustained for a long time. So you never see these fractures there. And we return back to the same solution. So that we're still not recreating our one single vent structure. Going back to the low permeability case where we expected, where we had obtained a conductive solution. Let's see what happens there. Same system, and now you see these fracture propagation due to overpressure generation, and they are usually released at the sill tips simply because the sills are impermeable in the solution in this implementation, and it has nowhere to go but the edges of the sills where it escapes from towards the surface. In this case, the smaller sills don't have access to much of the overpressure. Most of it is contained below this large sill structure here that comprises the main sill and is concentrated at the main tip. And what we end up here is a single big vent, at least, at the main sill tip, which matches the seismics. What we also notice here is that the time scales we're talking about here are very short. They're tens of years. I can play this again. And this is tens of years before this vent formation and this overpressure generation and escape is done. And this is very different from the hydrothermal plume formation, which occurs over thousands or tens of thousands of years, which also suggests that this is pretty explosive, also due to the overpressure and fracture generation, which also is expressed by the perturbed sediments we see in these vent structures in the seismics. So then we were very happy. We pretty much matched and using a simplified fluid flow model, could match the vent structure that we see in the seismics here. And what we tried to do then is to quantify how much of this gas that is generated in the system can escape through this vent structure. And this is a plot, don't really have to pay attention to it. But what it says here, depending on how much TUC is present there, the more explosive it gets, if there's more gas generated, and the more of the gas that is generated here can then be vented out here. So it goes from around 10 to 16% of the total gas generated can be expelled out of the system through one single vent. That's one single vent. What happens if you have many vents? Because this is just geometry. It doesn't mean that we only have one vent here. Like Ben showed, we can have many, many vents associated with a big sill. And we also know that these kind of events are usually associated with climate effects. So the Paleocene Eocene thermal maximum is associated with this region in the North Atlantic, and is also associated by negative carbon isotope excursion, around 3 per mil. And Sverre Planker and his colleagues had mapped out sort of how many the number of vents in the Waring and Mora Basin, which is very close to our model region, So what we did is we calculated how much comes out of a single vent and looked at the geometry distribution in the Waring and Mora Basin and the number of vent structures there, and tried to figure out how can we upscale that to basin scales. And this is what that actually looks like. If you take the TUC content going from 1 to 5, this is what the carbon excursions would look like. The blue is for generated methane, so the total amount of methane generated, and the yellow is for the amount that actually comes out. You'll notice that this one is higher than the generated, which is physically impossible. That's simply because the number we chose, or the number that was predicted for the Waring and Mora Basin, the number of vents, probably does not correspond to this. But what the takeaway is that you need TUC contents somewhere here, 4 to 5%, to drive a negative 3 per mil excursion. And that's using the easy row method. And this is a very simplified method where we say anything with maturity over 1, 85% of the TUC gets transformed, or of the carbon in the rock gets transformed to methane. If you do a more rigorous organophases kind of method, which is more industry standard, where we take into account the gas and oil generated from kerogen itself, there's a lot of inert kerogen in these systems, and that can reduce that. Moreover, the Cretaceous sediments, in which most of these sills, at least in the Waring and Mora basins are emplaced, have relatively low TUC contents, even when they're immature. The 200 HI and 200.5% TUC. So if we account for that and take into account also the organophases method, a more rigorous method of determining how much gas comes out of it, we only get up to a maximum of 0.2 per mil. So it's a bit difficult to explain the entire excursion based on the Waring and Mora basins, but we also note that besides the Waring and Mora basins in in Greenland and the Faroe Shetland Basin, you have much richer oil-prone rocks with more than 5-8% TUC, and these have also been affected by sills. So we need to really take care about that if we really want to quantify what happened here. Going back to quantifying vents and gases that I expel from it, we've only been dealing in 2D models, but for more accurate estimates for what happens in a vent structure and what controls vent geometry and their spacing around a vent, we need to up our game a little bit. We need to go to 3D. So then that would also give us a better constraint on how much degassing occurs and how much that affects the climate. This is a 3D model. It's not quantifying anything, but it's just an illustration of what we could achieve. And this shows how hydrothermal plumes are formed in a saucer-shaped sill over time. And you can see that they coalesce and have their typical structures. This only goes on for a few years, hundreds of years, thousands, sorry. But they're not gone to completion. And you can see they already start getting their typical spacing seen in this hexagonal structures that are formed in the isocontours or thermal contours there. The problem is that these kind of models, the 3D models, are very good to, let's say, answer research type of questions, like how much, what's its effect on its climate. But they're also, because they're also very computationally expensive, and the time-space resolution to resolve it correctly in 3D is kind of problematic. It requires a lot of time. So these kind of models are can be used to answer very specific questions, but they're not really suitable to incorporate into a general industry workflow. So what else can we do? We already have our petroleum system models, which there are different models. In this case, we have our own, it's called MIRA. And these kind of models take care of basin scale processes, like I showed you previously. So millions of years, kilometer scale. And it takes care of backstripping, so structural changes. I'm just backstripping this surface now, and I'm going back through time. and showing you how the surface changes. It also takes into account regional background thermal processes, so diagenetic processes based on basal heat flux. We have full kerogen kinetics here, and therefore can calculate how much oil and gas can be generated just diagenetically. And this is a map of oil expelled from a certain source rock horizon shown here. And if I on the video, we can also use very quick flow path migration, which takes seconds to minutes, to see how oil and gas migrates through time. So it's 4D with full mixing of oil and gas to show what's happening in the system here. But obviously, this kind of system still doesn't take care of sill processes. In order to try to better constrain sill processes, not where we have significant fluid flow and we really have seismic data that shows us that fluid flow is important. There we need to do some 2D or 3D models to better answer those questions. But if we can get away with 1D models, that's what we do. In this case, you obtain the lithological and the initial thermal structure just before sill emplacement from the basin model. So you can think about it as drilling a hole through the model and getting the data out before sill emplacement. That's my sill here that's being emplaced. See whether your calibration is correct with existing data. That all the 1D models again make it very easy to calibrate it to, for example, Retronite data or HI data or TOC data to see whether your initial conditions are correct. And then because these 1D models are so cheap to run, I can run thousands of models around my sill. I can run basically saturate this entire region with 1D models and then calculate, resolve in space and time correctly what the maturation is of my hydrocarbons in the system. And once that is done, I can send it back to my basin model and go on migrating any fluid that has been generated, hydrocarbon that has been generated due to sill emplacement itself. I'll just click on this now, and I'll try to stop it here. So this was all subsidence driven. I'm generating hydrocarbons and migrating it on the reservoir surface in time because simply I'm bearing rocks. And now my sill comes in and I start generating gas. And it's a different process. So I can successfully integrate, or to a very large extent, integrate the sill model into a truly basin scale model. And it takes advantages from both petroleum system model on basin scale and the 1D sill models on the resolution and times we need. So I think I'll stop there with this last slide, where I hope I've tried to show you that there are many questions we want to try to answer in such volcanic basins. And if we want to model it, I think we have to use the right model for the right question. 1D models are really cool. I like them. We can scale them up to basin scale, combine them like I just showed you, and get very far with them. But on the other hand, if there are clear expressions of fluid flow in the system, then we at least need to try to understand them and try to better incorporate them by either adding faults, pseudo faults in our basin models, or structural pathways that fluids can migrate through. But we need to get that understanding from 2D and 3D models, and then maybe incorporate that into basin scale models. But we really need to concentrate and try to figure out the right model for the right question. Thanks.
Thank you very much. I will start with the questions and the comments. The first comment is from Camilo Aristazabal, who has to leave the presentation, your nice presentation, and let you his best regards. And Octavio tells, amazing presentation, Iyer. You answer all my questions during the presentation, but there is one that I always have doubts. Can you estimate the amount of hydrocarbons generated and also how much migrate through the thermal vent and how much stay in the sill reservoir?
I wouldn't say I can model it 100%, but I can try to do that. But I have to take, in the 2D models, we're pretty good, I think, right now from all the industry work and the research work that's been done to quantify how hydrocarbons can be generated. So if I know the characteristics of my source rock, I know the kinetics, and I sort of know my sill model gives me the temperatures that I'm dealing with, I can get pretty close to how much hydrocarbons have been generated by the sill. But how it migrates through the system, that we have to test. We have to see. You can only play with scenarios, but that's the case in all petroleum system models. You try to answer it as best as you can using different scenarios, but you always have to ground that in what we see. So to some extent, I say we can, but how much, I cannot give you an answer. It will depend on how the system evolves, and each system will be specific.
All right. Okay, thank you. Nora Cesaretti, thank you for your talk. Excellent presentation. And well, yes, I feel the same thing that Octavio, that I have some doubts in my mind, and in the following, in next slide, you answer my question, the question I have in mind. So that means that the structure of the presentation was perfect. If you, is there any, let me see. Octavio said, as I said before, you answer all my questions. What do you think are the challenges to better calculate hydrocarbon generated? In Mendoza, we have several sills reservoirs.
Yeah, I think time temperature is an issue. So if we can, so geochemistry can tell us a lot. It can, and petrography. So if we can figure out what the initial heat input into the system is, so what sort of temperature, what sort of timing we have, or we can even sort of try to estimate it using, like I showed through the 1D models. We have observations on Retronite data, for example, and then we can try different scenarios and see what gives us the best match, and then go back and see, does this make sense geologically and geochemically? If it does, well, great. And then you can use that temperature profile to calculate hydrocarbon generation. I think it's all doable, at least to get a good quantitative answer to it. I hope I have sort of answered your question. I cannot calculate one for you right now, but if you give me the kinetics and some sort of data that I can compare to, like Retronite data, I can happily try to do that.
Okay, so thank you again, Karthik. Estamos terminando la sesión de hoy. Nuevamente queremos agradecer a Ben y a Karthik por su tiempo y calidad de las presentaciones, excelentes presentaciones, y a todos los asistentes que se unieron a este evento y participaron con las preguntas a través del chat. Antes de despedirnos, les comentamos que la próxima sesión de este ciclo de conferencias 2021 será el jueves 4 de noviembre, corresponde al ciclo de microsísmica, que tratará sobre el tema Key Insights Gained from Induced Seismicity Monitoring in North America Shale Plays, a cargo de Darío Baturán, de Nanometrics. Y por último, estamos anunciando nuestro último webinar del año, el último del 2021, en este ciclo de magmatismo. Será el jueves 16 de diciembre y tendremos una presentación a modo de cierre a cargo de todo el comité organizador del simposio de magmatismo y sistemas petroleros del Conexplo. Así que, sin más, agradecemos a todos los presentes y nos vemos el próximo 4 de noviembre. Y thank you very much, Ben and Karthik again.
Thank you all. Thanks again to the organizers. And sometimes questions come later. So if you think of any, please feel free to contact me.
Yeah, I'd also like to thank the organizers as well. And just as Karthik said, if anyone wants to send me a question as well, just send me an email. And